Good morning. This is the original painting that Escher made in 1964, and it's called Square Limit. We're not going to do this because this is too difficult for me. So we're going to do a simplified version of this, which is going to look something like this. Cool. Let me just quickly introduce myself. I think I have another. Can you see all right? Like even at the back? I can make it bigger. Bigger? No bigger? Okay, perfect. So my name's Drew. I work for a company called No Red Ink, where we basically teach writing for kids in school. You can find me online as Arkham with a 4, and we're going to build this painting today. But before we start, I just want to tell you about this paper. And I know it's boring, it's a paper, but it's a paper called Functional Geometry. The original version, I think, was like in the 80s, 1982, and there's a like updated version for 2002. And I think this paper is amazing, and hopefully by the end of this talk, you'll agree with me. And I just think like the idea behind functional geometry is just like something amazing. Okay, so I promised we're going to do a little bit of Scenic. There's not too much Scenic in this talk, so guess what? I lied. So I'm going to show you this. I have an app here. I can run it, and it says hello. And I'm just going to quickly show how it works. So how many of you are complete beginners in Elixir? Perfect. Great. So I'll try to explain my best. Feel free to interrupt me at any point. Just yell and I'll stop. This is the mix EXS file. So this is where usually you specify all the dependencies of your Elixir apps. And you can see that between the dependencies, I have Scenic, which is this graphic library, and the OpenGL driver for Scenic. Okay, and normally in an Elixir application, you have this function which is called application, which specifies the entry point of your app. In this case, is Scenic Escher. So I'm going to open that, Scenic Escher. And you can see here, even if you don't really understand how this works, I think it's like pretty straightforward. Like we're grabbing some environment information for Scenic Escher, and it's about a viewport, which we're all familiar with, and then we specify a series of processes that we want to boot up, and then we're saying, okay, supervisor, you start these children. Okay, so I'm just going to quickly show how the configuration looks like. We have config Scenic Escher, and we are specifying a viewport, and this is like these sides. We're saying which is the first scene, so this is the entry point of the Scenic application, and here we have the driver that we're using, which is the OpenGL driver. Okay, so now this is the real core of the app. And you can see now it's like quite simple. We're just using some Scenic libraries, like modules, and we're building a graph that is a font size, a theme, and we're just typing hello. And in the init function, we register this process with its own name. So in this case, it would be Scenic Escher scene home. And we push the graph into basically the Scenic world, and Scenic will take care of rendering it. I have a confession to make, which is I've hacked Scenic to implement live reload, but sometimes this crashes my laptop. So I'm going to show you like all the things under the hood. So I have a bash script that sleeps 300 milliseconds, and then if it has this heuristic, if something is completely wrong, it will just kill everything that looks remotely like a beam process. Thank you. So I'm going just to show you hello Prague, okay? And I save, and hopefully this should pick it up and refresh it, okay? Thank you. And of course, this is Elixir, right? So we have this amazing capability of observing a running system. So in this case, I'm just going to do observer start. I mistyped that, start. And you'll see the familiar look of the Elixir observer. I'm going to zoom in, don't worry. You don't have to read everything about that. But you can see there's like this high-level vision of like what the system is up to. And you can see there's like this, wow, look at this zoom. Scenic, right? And then you can see if I go on this side, there's like a cache registry, main viewport. This looks familiar, right? This is exactly the thing that we've configured. And then there's Scenic, Escher, Scene Home. So the wonderful thing about Elixir is, it comes in with this strong belief in fault tolerance. And therefore, the way that I've implemented live refresh in the code is that I've used a library which is called xsync, which picks up file system changes. And then I've hooked up this little process, which I've called refresher, which as soon as it picks up a file system change, will find the scene, kill it brutally. And then the supervision system will reboot it, and this is how I achieved live reload. So if it crashes, like you know why now. Awesome. So I've said this. So how much time do I have? Okay, just 5 minutes, great. So I'm going to be a bit boring for next 5 minutes, but I really beg you to try to keep it together for the next 5 minutes, because that's completely necessary to understand the rest of the talk. I call this an owl talk. Like if you miss the circles, then at some point you'll see the owl and it's like, oh, what happened? So just be careful about the circles, and the circles are going to be boring. You'll be, oh, I've been doing circles my whole life, I know how to do circles, but you'll realize this is not the circles like you've been looking for. Okay, so let's do this. So I'm going to explain vectorial algebra, something like that. So I'm going to create a vector. I'm going to call it V1, and I've written these like little modules that are able to create data structures. So just like added a little bit of like sugar magic in front of that, and then I can do something like vector build 1, 2. Okay, in this way we have these two vectors. And the great thing about these vectors is they describe a movement in space, but they don't really describe where the movement starts. This is just a movement in a direction, in a certain length, but we never say where the movement starts. And this is going to be fundamental. In order to explain this concept better, I found this amazing web app, which is called JS Paint. And we have V1, which is a vector which goes on the x-axis, 0, and 1 in the y-axis. So it's something like this. Look at my amazing drawing skills. So this is V1, and then we have V2, which goes right by 1 and up by 2, right? So we have something like this. And in vectorial algebra, when you sum two vectors, you do something that we learned to do as kids when you don't want to go around the corner, you just want to cut through, right? So you get something like this. And this is the result of doing this sum operation. And in this module that I've created, you can just do vector.add v1, v2. Okay? And we get exactly the same. Like we go left and then up by 3. This is pretty boring, right? But for example, like we could take something like this and we could say vector dot scale, and we can say 2, and we can wrap this a little bit. Perfect. And in this case, see, we've just made this bigger. It's going in the same direction, it's just going twice the length. And I think up to this point is pretty boring, but there's something which I think is quite cool. It's like if you have a vector like this, how do you get a vector like this? And if you think about it here, for example, we have something which is 1, 2. The opposite is just -1, -2, right? So, for example, if I take vector and do neg on V2, we get exactly that. So the negation operation creates this opposite vector. As I promised, this is like the boring part of it. And the other weird thing is that we're going to use this pretty weird box model. And the box model is composed of 3 vectors. We're going to have the A vector, which connects the origin, so 0, 0, to a certain point in our world. And this A usually tells us where our drawing starts, because we're using this box to control where the output is going to be. Then we have another vector, which is called B, which I use the mnemonic base. This is going to be the base of our drawing. And we have a third vector, which is vector C, which stands for I don't know what it stands for, but my mnemonic is side. I know it's not the same letter, whatever. Okay, so we have this box model, right? Cool. So this is where the boring part of the talk ends. So if you haven't followed so far, I don't know what to do. It's like you're screwed, basically. Okay, so I'm going to create a box, and I have like a little bit of snippets, just like to make like the horrible part less horrible. And you can see we create a box. It's just an Elixir struct. We build a vector that goes from 0, 0 to 75, 75, and then B goes from goes right by 400 and stays on the same y-axis, and C goes up, right? And here I can just call another snippet, which I've created. I'm going to explain this. So we use a module called fitting, and this is because I don't really want to, especially when I'm live coding, I don't want to type 475 a bunch of times. Like, I think 0 and 1 are perfectly good boundaries. So this fitting just basically does that. And then we have this box that we just created, and this is the interesting part. We have picture dot open close parentheses. So if you're new to Elixir, you're like, oh, what's this? Like, normally I call functions just by opening and closing, right? And this is a way that you call anonymous functions in Elixir. And if you're wondering something like, why are there 2 ways to call functions in Elixir? I don't have internet, but if I had that, you'd be redirected to this amazing Stack Overflow post by José that explains why. So if you're curious, just do whatever I did, but with internet enabled. And then once I do that, I call this function, I get some values, and I have this module which is called rendering, which transforms my simple data structures to things that Scenic can operate upon. So for example, something that Scenic can operate upon is a path. You can just basically tell like it's an SVG path. You say, start here, draw the line there. Okay. Okay. So now I'm like, okay, this is boring, right? Let's go back to the C. Oh, look, beautiful. So this is exactly what I've done in JS Paint. And this is A, then we have B, and then we have C. And now I can write like a simple line. For example, I can say I want to draw a line, and I want the first part to be a vector from 0, 0, and I want the second vector to be a vector from 0, 5 to 0, 5. I'm sure I made a mistake. I've hooked up, I spent last night hooking up Elixir language service, like server. So this should work now. Amazing. And if, perfect. You can see that now we've drawn a line between the origin and 05, 05. And of course, we're not just limited to lines. We can also draw polygons. So I'm going to draw a polygon here. Polygon, and I'm going to say that here we're going to I hope I don't mess this up. It's going to be fine. Vector build of 5 0. No, I messed something up. Let's see what the error is. Syntax error between. Okay, I have a double paren, like double comma. Beautiful. And you can see now we have these 3 points, and these 3 points are going to generate a triangle. I think. Let me quickly do. Oh no, it was there. I just didn't have enough faith in computers. Cool. So we have this polygon. You can see we start from 0, 0, then we go to 05, 05, then we go to 05, 0, right? And this way we're drawing this polygon. But triangles are not like that cool. So instead, maybe we can draw a letter. So I've created this little module which is called letter. And for example, this thing exposes an F. And when I do that, you can see we show an F on screen. But this is not magic, because if I just go inside letter, it's just a polygon. It just has like more edges, right? It's the same thing. Like, you know, it's all fake. There's no truth. Okay, so we have this letter, right? And before I said, the picture is a function. And you're like, what? Like, I spent my whole life thinking a picture was just a picture. How come a picture is a function? And the advantage of having a picture as a function is that you can do pretty amazing things. So the thing that I want to make sure that is clear is that usually a picture is a function, and it takes a box and returns a list of something. right? So usually I'm taking a box, I'm returning a list of paths. And the reason why this function takes a box is because in that way, if I manipulate the box, I can manipulate the picture for free. And what I mean by that is, for example, if I change my box to be the B vector that we talked about, and if I save this, we'll see that something will happen to our picture. Right? And if you think about it with your programmer brain, you're thinking, well, if I had to do this by manipulating the F itself, it'd be pretty hard, right? Like you're doing this projection sort of way, right? And for example, I could do the same thing here. And instead, in this way of representing a picture as a function, you can do these pretty complicated transformations for free. And for example, something else that is quite hard is to do a rotation, right? Because then you have to go into angular magic, dark magic. But instead, if you manipulate these vectors, bam, for free. Okay, I hope that wasn't too much, but I'm just going to go back to a good reality where the axes are normal. Perfect. So I said that we could write a function that does like these magic things. So let's do this. I'm going to create a function which I call term box. And inside this term box, I'm going to do fm box. And I'm going to do something which is a bit weird, but I will explain it. So I'm just going to type real fast for like, a few seconds. Vector add, A, B, then B is going to be C, and C is going to be vector neg of B, okay? And then I'm going to call this function like I did before. It's going to be term box, open close parentheses. This is like the way you call an anonymous function. And you'll see what happens. What? Luckily, JS Paint to the rescue again. So let's say the first thing we did, A becomes A plus B. And look at my amazing drawing skills. So this is the old A, this is the old B, this is the new A, right? Then we have B, which becomes the old C. So the old C was this thing which is going upwards, and this has become our new base for our image. And the side, the C vector, is the old B just negated. Since the vector doesn't include where it starts, if we just negate it and change the origin, we basically get like this image, like this mirror vector for free. And this is exactly what happened here. So by manipulating this box, we're able to turn this picture. But I think this is quite intrusive, right? Because like in order to change this picture, we literally had to change the box, and then we pass this box to a function. So a better way to think about this is having a function which is term picture. And term picture is just something that takes a picture and returns a nested function. And the nested function is what operates on the box. So once we receive this box, then we can call term box on this, and then we can call the picture itself. This is going to be like a little bit weird, right? Like because we're getting this picture from somewhere, we're creating a new function that returns, like we return this new function, takes a box, turns the box, and then applies the picture that was passed to us. But I hope this is going to make sense. So let me just copy this and I'll move it a bit down. So now just for presentational purposes, I'm going to disable the turn. And perfect, that thing has gone back to normal. And now I can turn the picture again. And you will see this is exactly the same thing, right? But the great thing about this is that now we have expressed in a function this idea of turning an image, right? So if I had to repeat this twice, no problemo. Or, another time, no problemo. Or another time. And you're all thinking about something. We can optimize this code with doing this. Okay, but hopefully, I think this is like a pretty good example of like how when you frame a problem using like a functional idea, you can make really hard problems very easy, but you have to find the right abstraction for it. So I'm not going to bore you about building like all the different types of transformations. I'm going to share the code later so you can check it out. But basically, I create this module called picture, and you can check it out. Like there's all these like turn functions, flip functions, and things like that. I'm just going to show you a couple of things that we're going to use. So I'm going to comment out this code. And And here, like for example, I can do the same thing we did before just by calling turn. So I've just exposed that as a module function instead. Okay, cool. Let me check my time, 1927, perfect. So we're going to call this fish. Like, why fish? Fishy shapes. Vim, let me exit. Okay, I've broken it, of course. And then picture is fish. Perfect. This is the main tile that's going to implement the whole painting. There's no other tiles involved in this talk, and no tiles were harmed in the preparing of this talk, I think. So we have this fish, and you'll be, oh, it looks like a bit weird, like, you know, like someone that can't really draw did this. But I will prove to you that this is actually really cool. But before we do that, I'm just going to show like a couple of small functions that I created. It's like one is called above, and you can pass 2 pictures to it. And what it does under the hood is that it basically takes the original box, splits it in 2 boxes, and puts one up and one down. So if I do this, you'll see this is what the function does. So it takes like these 2 pictures, takes the box, splits it like in 2 halves, and say, okay, this is one and this is the other. And just as above, there's also another function called beside, which does a similar way, just parallel, right? So just like side by side. And once you have that, you can have a quartet, which is just 4 fishes. Well, in my case. And if you have a quartet of fishes, this is what you get. So you basically get 1, 2, 3, 4. Okay? And all this is, and actually quartet under the hood is implemented using above and below, right? Like above and beside. You just make 2 rows and then split them up together. You'll be able to check out the source after the talk. Okay, we have this quartet, and also we have an ability of putting tiles like on top of one another, and this is using over. So I can say you can put a fish, and then for example I can say take the same fish and turn it, and then turn it again. You'll see what this generates. That's pretty cool, no? Let me just do this. Maybe I'll move this on this side. Perfect. And you can see that the reason why the fish is made in this weird way is because it has very interesting geometrical properties. So I've just taken the fish, I've turned it twice, and you can see they perfectly match with one another. And this is the whole trick that allows for the creation of the whole painting. So if we have a picture here, this is our sort of like little thing. And I want to show you now how the original painting looks. And if I zoom, you can see that, for example, now what I want to focus on is this central bit. You can see there's like these 4 fishes. But as opposed to my fish, which is like the fish is like diagonal, actually these fishes like on the left, they're straight, right? So I need to have a function that basically makes this thing a little bit straighter. So I'm going to do that, and I'm going to show you how. So I'm going to call something tossed, and I'm going to take the fish and call a function called toss, which will basically turn it and make it like a little bit smaller. And now I'm going to do an over, not of fish, but of tossed. Tossed. Perfect. And now, okay, so we've created this little fish, and then we turned it 4 times, and we just put them all one above one another. And this way we got something which is very similar to the central piece. But you can notice there's a slight difference, right? Like this central piece actually is like the fish is in the wrong order, right? Luckily, I can do this. I can take the little bit and just say flip this vertically. And if, oh no, thank you. And if I do that, you'll see that when the picture upgrades, this is exactly what we had on the left-hand side. And this is what I will call a square from now on, because I like to think there's just like these 4 fishes. So I'm just going to call this square. Square. No, this is not how you type square. This is how you type square. Perfect. The other thing I want to show you is how to build this part. If you look at this, you'll see there's like another tile there, which is a normal fish, and then there's like these 2 small fishes, right? And I will call this triangle, because if you follow the fish, it looks like a triangle. And this is very similar to the other version. So I'm going to say triangle is over of the original fish. Then I'm going to take the tossed version, and then I want to rotate the tossed version 1, 2, 3 times. So I'm going to do tossed 1, 2, 3. And I'm going to say that the picture is the triangle now. Okay, and now my syntax highlighter complains that no one is using square, but don't worry about that syntax highlighter. And you can see this is exactly that tile that we had. And this, we have the square and we have the triangle. And now if you look at this painting, that's really all that we need. There's no other tiles. Like all the other tiles that we can see, there's just smaller versions of that. So if I zoom in a little bit more, you'll see like this is a smaller triangle, and this is a smaller square, and this is a smaller square, and so on and so forth. So the nature of this painting is recursive, and these are the 2 like building blocks that we need to build this painting. So now I want to focus on this other bit. If you look at this side of the painting, you can start to unpack the recursive nature of it. On the bottom, we have a triangle. This is a flipped triangle. And here, we're basically like doing the round of recursion, right? We're going like, you know, like Inception. We need to go deeper. So we're going to do that, and I'm going to do that using something which is not very orthodox. So I'm just going to create another instance function, which is not nice. Don't do this, but I just want to do it because I don't want to define a new module and all that. So I'm going to call this side, and this side is going to be a function, and I want to pattern match this function on 2 cases, because when I build this function, I want to pass in the depth of how much recursion I want the function to do. And there is a very simple case where it's 0, and when it's 0, I basically want to say, oh, don't do anything at all. So I'm going to type in a blank function, and a blank function is something that takes a box and returns empty list. Okay, and in the case where someone asks a side with depth 0, I'm just going to say whatever. There you go. And instead, if someone gives me a proper number, which is not 0, I'm going to do something. So I know that this looks like a quartet, right? And the top 2 things, if I look at them clearly, they're exactly the same tile. They're not flipped, not rotated, nothing. They're exactly the same type, which is the next level of the recursion. So I'm going to type exactly that. I'm going to say this is a quartet, and then for the next level of the recursion, I'm just going to do side.n-1, and here as well. And then we have to see the left-hand side. This was the rotated fish. So I'm going to say, sorry, the rotated triangle. So I'm going to say triangle turn, and then we have our original triangle. Okay, and now I'm going to say that picture is side of 0. And unsurprisingly, this is nothing, right? So this is not very cool. But what if I make this 1? We can see this is already looking pretty good, right? We have these 2 triangles, so they're flipped in the right way. And then when we go the level up, we hit the base case of the recursion as just nothing. And if I do 4, you'll start to be, whoa, hopefully. Thank you. and you can see like this is like what happens. Like it basically it starts exploding, right? And you can see like I've kept like this debugging information about all the boxes. So you can see all those like red lines are all the A's. You know, like we've seen 1, but now there are already probably 100 in there. And the complete picture, there'll be thousands, I think 30,000, something like that. So I think this is like pretty cool, right? Like we've come up with this model and we've written a recursive function, and now the recursive function, you know, has a life on its own. And we can see that in this way, we've basically implemented this side bit of it. Now I want to focus on another bit. And the part I want to focus on is this tile. If you see this tile, you'll recognize there's something interesting. So the bottom right is clearly our square. The top right is our side. We just built it, right? The bottom left, this thing, is just our side rotated once. And what about like the top left? This is just like the recursive case of the corner. So we're just going one level deeper. So I think, you know, like, I think this is the beauty of it. Like once you look at the problem in this way, the code becomes like quite trivial. So I'm just going to do a thing I love, which is copy pasting code. Just kidding. And in the case of 0, this is the same. I'm sure I'm going to do a mistake now because I copy-pasted code, but whatever. So I think the top left is going to be a corner, then we have a side, and then the one on the thing we said is a side turned, right? And then we said that the last one is a square, okay? And here I'm going to do a corner instead of a side. Oh no, there's no square. Oh, thank you. Beautiful. And you look, this is exactly like what we wanted to do, right? We have like this square, we have the side, we have the turned side, we have the recursive case of the corner. And really, now these are the two like meta components. I've read this blog post recently about how to optimize a game to run like in 64 kilobytes of memory. And this is like something that they use quite often in these like old school games, is to create these tiles and then create this group of tiles. And in this way, you can basically save memory because you don't have to specify each pixel individually, which is going to render, but you just create these abstractions over your game level like tiles. I'll send you a link later. It's really cool. You should all read it. So now I want to show you something else. And this is the last thing, actually. So we have this painting. And if you look at this painting, we've always looked at these quartets, so these grids 2 by 2, right? But in this case, if we look at the whole painting, we can see there's another pattern. Like this could also be seen as a 3 by 3 painting, right? And what I mean is that this is the first row. These are the first 2 rows. This is the whole painting. This is the first column, second column, you know, grids. I mean, I don't have to explain them. If we look at those and we think at all these building blocks that we've been building so far, we can see that we basically have everything, right? Because this thing is a corner, this thing is a side, this thing is a corner, we have a side, this is our square, we have a side, corner, corner. Okay, so it all is a matter of like, you know, like the next, like the level outside of that is like a recursive function. So we're going to have to do that again. So I'm going to type this actually because I don't want to mess it up. So I'm going to call this square limit. It's going to be a function, and just as before, in the case when it's 0, it's just blank. Instead, when it's not 0, I'm going just to define these little building blocks. One is going to be the side, and the side we'll know is side of n minus 1. And then we have the corner, which is at corner, okay, n minus 1. Perfect. And I think a nice way to think about this is just think northwest, north center, northeast, and like do them all together. So I'm going to just like type them all like that. So I'm going to say northwest, north center, northeast. No, I made a mistake already. Middle west, middle center, middle east, southwest, south center, southeast. Okay, and we have these 9 tiles. And the way I'm going to hook them up all together is I'm going to call a function which is very similar to quartet. The only difference is called no-net because it has like 9 of them. And I'm just going to do something like, no? I don't know how to use Vim anymore. Just give me a sec. Okay, I got it. Perfect. something like this. I'm not going to save, otherwise my syntax highlighter is going to complain a lot. But let me just move this on the side. So we remember that we just built the corner. So like the top left thing, the northwest, is actually the corner we just built. So I'm just going to say corner. Okay. The north center is the side we built, side. Northeast, this is our corner, but we turned it 3 times, right? Sorry, corner, and I'm going to turn, turn, turn. Cool. Now we have the middle west, that's the side turned once. Turn. The middle center is just our square. Okay. The middle east is our side turned 1, 2, 3 times. So I'm just going to quickly copy this, paste it. Oh no, I knew I made a mistake there. Okay, cool. Oh no, I made a typo as well. Turn. Okay, cool. Turn. Oh my God, this is horrible. Okay, calm down, Drew. So the last things is like the last layer. We have southwest, which is a corner, just rotated once. Then we have south center, which is a side rotated twice. Turn. And also, I've been reading DHH's tweets, so if I make mistakes, I can just blame it on the Apple keyboard. Corner, and here we just need to turn the corner twice. So I'm going to do the corner and corner turn twice. X. Okay. And now if I look at our end result, now it's still looking like the same because I didn't change the code. But if I change this to be a square limit, we'll see what happens. And now this is my computer processing all this. Thank you. But like, I think the thing I like the most about this idea is that think of how many off by 1 errors you do when you're implementing this programmatically, right? Like you're just like trying to put things in a matrix and each thing has an index and you're trying to manipulate them and turn them. And if you think of the problem in that way, it's so easy to make mistakes, right? But if you think of the problem in this functional way, you can see that once you have this idea of a box, then this idea can just explode like almost infinitely, and you won't need to worry about that anymore. Just before I finish, I just want to show you this, which is you can find my Vim configuration files if that type of person, but the core of the talk is the Scenic Escher, and you can check it out. It's on GitHub. Also, like if you're interested in Elm or functional programming in general, come talk to me. If you want to work for my company, I'll help you apply. And yeah, that's all. Thank you.
Thank you very much. Okay, so I think we have room for maybe just 1 or 2 short questions. Anybody? No. Oh, here is one. Yeah, okay.
Hi. Can you briefly talk about the? You mentioned that the basic fish structure has like some qualities to make it like. Did you draw this in the fish yourself, or what are the basic qualities for that?
So I really recommend that paper I was talking about, this functional geometry paper, and it tells you about all these basic operations, and then it explains why this fish is special. Something which I love is you can Google for Escher original carvings, and you can see all his iterations of these patterns, and you can see the reason why he built this fish in this particular shape, because it's easy not just to combine them on a 1-by-1 level, but also in these 2-by-1, right? And this is like the trick, like the only reason why the painting works is because in the triangle, we're able to go to a small, like to the half version of it, right? So there's like a lot of like nice content like out there. Another website I can really recommend, it's a bit weird. It's called Tessellation. Oh, I don't have internet. I forgot. But if you just Google tessellations on Google, you'll find this link. And this website looks like it's coming straight out from GeoCities, but it has the best content on tessellation they can ask for. And it's all these ideas on how you create this fully coverage of a surface using a single pattern, and also explains how you can achieve this sort of nested, like going to the infinite sort of thing. But I really recommend this paper. I think it's just so good. And once you've understood the principle of it, then you can apply it to every sort of programming language. I just used Scenic because I wanted to play around with it. I thought it was just nice as an exercise. But I think the great idea is just this functional geometry, thinking of the problem, this different world, and it just simplifies the problem so much.
Any luck trying to recreate Escher's paintings on perspective?
On perspective, for example, the infinite stair or
yes.
things like that. There are interesting papers. I was researching this thing. I think it's just there's two aspects of Escher. There's Escher, the sort of impossible artist. He's trying to make these images which can't exist in reality. And there's Escher, the tessellator. And you can see there's even if you look at the Escher paintings, you can instantly recognize which one of the two is one or the other. And I think this approach works very well for these tessellation problems. And instead the infinite, the impossible things are more perspective tricks, right? So I think you'd have to come up with a different idea. I can send you some papers. I've done some small research. There's also an amazing paper about two computer scientists that finished an Escher painting. So there's a very famous Escher painting that is this sort of recursive nature. And then in the end of it, Escher just drew a white circle because he didn't really know how to finish it anymore. So two computer scientists, they came up with a mathematical model to model that, and they actually wrote a computer program that generated the right center of that painting. And I thought that's such a great idea. So I'll try to collect all these things and post them somewhere. Yeah.
All right. Thank you very much.